Okay, so welcome everyone to the Northwest Database Society. Today is my great pleasure to introduce Professor Gerome Miklau from the University of Massachusetts Amherst. Gerome, he is an expert on various aspects of databases related to society, especially security and data privacy. But he works on all sorts of aspects, including forensics of databases. One of my favorite papers is on how you can actually recover deleted records from Postgres or from MySQL. Look up that paper. It's a very fun paper to read. In the recent years, Gerome became a leader of applying differential privacy to real-world applications, and this is what he's going to talk about today. So here is Gerome.
Thanks, Dan. Thanks. It's good to be here, everyone. Hi. So today I'm going to talk about system support for designing privacy algorithms. So I work in a model of differential privacy, and I'm going to try to explain in the first part of the talk sort of like what's complicated about understanding how the performance of differentially private algorithms. And in the next part, the second part of the talk, I'm going to talk about our emerging work on a system for supporting people in building differentially private algorithms, hopefully people with less skill than the experts. So I'm going to review just the basics of our privacy model. The setting here is that we're trying to manage sensitive data, that is personal data that is about a set of respondents and that is collected by a trusted curator. And we're interested in managing sort of the boundary between the trusted curator and this untrusted analyst, who may not be, may not have bad intentions, but may perform analysis of the data and reveal something sensitive about the respondents, something that could do them harm if it was fully exposed. So the goal here is generally to support the release of aggregate properties. So allow the analyst or anyone looking at the analyst's results to learn, for example, that diabetes and obesity are correlated in the population that's being studied, while at the same time preventing sensitive facts from being disclosed. The fact that some particular person has diabetes, that should be protected. So the formal definition of differential privacy is here. A differentially private algorithm has to be randomized, and we say it's epsilon differentially private. Epsilon is a knob that we can turn to control the strength of the privacy guarantee. If for any two neighboring databases, the probability of the outputs on D and D prime is almost the same. And D and D prime differ by one person's information. And the rationale behind this definition is that if you're deciding whether you're willing to opt into the database, this guarantee is saying that anything released about the database is almost the same. If you opt in, it's almost the same as if you weren't there. Okay, and so then you can feel comfortable opting in, and we're going to protect your privacy. This isn't a talk where I'm going to go through this definition in a lot of detail, so I want to just make some high-level points about the implications of differential privacy. So the key thing for the respondent is that they get this guarantee about what could be learned about them, and really it translates into a limitation on any potential harm that could come to them as a consequence of releases from the database. And it's a very strong guarantee. It's a little bit of a complicated guarantee to understand, but people seem to believe that it's if we can provide this guarantee, it's a good thing, and that people are safe to opt in. To the analyst, it places limits on the computation that can be done. And so the cost of offering this guarantee to every individual is that the results that we release about the database have some noise in them, okay? And our primary goal is to build algorithms that satisfy this definition and introduce the least amount of noise and are, in other ways, as usable as possible by the community of analysts. So the definition was proposed a little over 10 years ago now, differential privacy, by theoreticians, and it's taken a while, but we're now seeing significant adoptions of this definition and deployments in practice. There was actually a rather groundbreaking deployment back in 2008 by the census, But that was a rather rare, rare example until recently. And now we have Google and Apple using differential privacy as well as the Census Bureau, exploring how to deploy differential privacy more broadly in their products. So despite the fact that we have a few good examples of adoptions of differential privacy, the truth of the matter is that each of these examples required a team of experts to take the technology and apply it to a specific application. And a big emphasis of our recent work and with my collaborators has been really to expand the potential for the deployments of differential privacy and remove some of the obstacles to adoption of differential privacy. So, and here are some of the obstacles. So the practical performance of privacy algorithms is really complicated, okay? Users can't understand how these algorithms perform, when they're going to get accurate results, when they're not going to get accurate results. And they're, in fact, in some cases, poorly understood by researchers. The research community also lacks a rigorous methodology. And the first part of this talk is going to be an example of a kind of like benchmark and a set of principles that we put together to make the analysis of algorithms more rigorous. And the last thing is, like I said, it requires a team of experts to deploy differential privacy. So the second part of the talk is going to be about how we can make it easier, how we can start to move towards a system that will allow people to write private programs that are accurate and efficient. Okay, stop me with questions anytime. So as I mentioned, we always want our algorithms to satisfy differential privacy. That's like a bottom line. We don't want to consider algorithms that fail to satisfy the privacy condition. So, you know, everything has to meet the privacy condition. But subject to this constraint, we're optimizing primarily for accuracy. That's our main performance metric. So it's a little bit different than probably a lot of the work you do where you're optimizing for computational efficiency, maybe. We care about, I mean, we care about computational efficiency, but usually it's a, you know, sort of a faraway second concern to accuracy. And, you know, to a first approximation, these are the things that contribute to accurate privacy algorithms. The first two are really things that measure the kind of like signal strength that we're allowed to have. You know, so when we analyze data under differential privacy, we're bound by this privacy parameter epsilon. And we often refer to this as a budget because the higher the epsilon, the less noise you're going to have in your results. Okay? And it's also the case that the more data you have, the more accurate inferences you can make. All right? We often think about error you can think about error in terms of like population percentages. A lot of the things we're computing on data are statistics about the population, like how many people satisfy this property. So if you've got, you know, if you've got properties that are pretty rare in your population, it's harder to learn about them accurately because you have to add noise. But if they're, you know, the noise is sort of an absolute, and for given epsilon, the noise scale is sort of absolute. So if you can gather 10 times as much data, then that rare population is probably going to get bigger. And in relative terms, the noise is smaller. So you can learn something about that rare population. So these two things, actually, we showed that these sort of like behave exactly equivalently. You can trade off your epsilon budget for gathering more data. Okay? So the other component is cleverness. So if you design carefully a good algorithm, you can get more accurate results. I mean, that might seem confusing because we've got this privacy standard that we have to adhere to. But the fact of the research right now is that we don't have universal mechanisms that are sort of like optimally accurate for a given epsilon. If we did, then we'd just use that mechanism and we'd know, you know, we know which algorithm to use and we'd be getting the best results we can. But the space of algorithms is complicated and there's all these different tasks that we might want to do, and we don't know what the best algorithm is among all of those that satisfy the privacy condition. Then I threw in computation here just because I think that as time goes on, this is going to become more of a factor, but there aren't too many algorithms. So what I mean here is that, you know, if we had more computational power, could we get more accuracy? So this is the signal strength. And this is usually in short supply, right? Data is expensive to collect. And the privacy budget is sort of like imposed on us by somebody. It's like a policy, like how trusted are you to analyze the data? So those things are a little bit hard to get more signal. So my job is to develop clever algorithms. And it's usually worth it to, work on cleverness because it's easier than trying to get more data, okay? Question, yes?
You design different algorithms for different epsilon budgets or for different things that the analyst would be asking, or? Yeah,
it's a great question. So most often for different tasks, definitely, different algorithms. And I'm going to show you some empirical results that will answer your other question, whether we need to use a different algorithm when the epsilon changes. And the answer is yes, but that's not something that was really well understood until recently. Yeah, another question, yes?
Oh, how would more computational efficiency make things more accurate? Wouldn't it just make things run longer or take longer?
Well, yeah, I mean, my point here was that most algorithms are not constrained by computational limitations yet, at least the class of algorithms I'm looking at here. There's some instances where, if I had a faster computer or a bigger cluster, I could, what I mean is that some of these algorithms have to solve hard computational problems in order to get the best results. And so more computation will help a little bit, but usually we will run longer to get as accurate results as we can, and we're not too constrained by that at this time. This is evolving. It could change. Did you have a question in the back?
Yeah. Like you were mentioning on the previous slide, where one of the bottlenecks in adoption was the fact that the algorithms don't perform well, right? So I'm just curious why you put down computational efficiency as a secondary metric here.
Well, so when I say practical performance of privacy algorithms, what I'm really talking about is accuracy. And that language is a little ambiguous. I should have clarified that. So the performance metric we care most about when we're studying these algorithms is how much noise is added or how accurate the results will be. And it varies a lot, and there's complicated relationships. Yeah. Okay. So here's a chart which shows the relationship between error on the y-axis and one measure of signal strength, which is the privacy budget epsilon. Okay, so there's always, for any algorithm, a trade-off. I can run my algorithm for any epsilon. The higher epsilon I run, the lower my error will be, the more accuracy I'll get. The lower my epsilon, the stronger the privacy guarantee, but my error is higher. So there's always a trade-off. But a better algorithm gives us a better trade-off for any epsilon. Okay, so for a particular task that I'm going to tell you a little bit more about later, these are some algorithms. This is like the original algorithm, the Laplace mechanism proposed in the original paper. This is Dan's work, actually. Dan's surprise. This is Dan's best privacy algorithm that we worked on together in 2010. Here's the multiplicative weights exponential mechanism, which some of you are familiar with. And here's another algorithm that is actually one of ours. So you can see over the years that cleverness is getting us better results. Okay? We're devising new techniques, exploiting new features of algorithms, and getting the error down for the same level of epsilon. So all of, if we look at this point right here, these are all algorithms that are all providing 0.5 epsilon privacy. What distinguishes them is that some are more accurate than others. Yes?
Are there lower bounds or any sort of way to gauge how much room for improvement there remains?
Yeah, that's a great question. There are definitely some theoretical lower bounds known for certain tasks. The problem is that in practice, how to instantiate them for real data sets. There's constant factors, there's asymptotic behavior. It's really hard to get concrete bounds for this data set on this problem. And so that's one of the challenges of working on these algorithms in practice. Yeah.
What are the units of the y-axis? Or yeah.
Don't worry about that. I mean, that's a good question, but I'll be more specific on some of the later experiments. This you can think about as like population. The error is we're normalizing error so that it's like in terms of population percentages. So if you see a number, this is like 10 to the minus 2 over here. So if I have this kind of error, it means like relative to relative to a property that I'm testing that 1/10 of the population satisfies, 10 to the minus 2 is low error, pretty low error. It's 1/10 of what I'm trying to measure. But relative to a property that, you know, 10,000th of my population satisfies, it's going to dwarf the signal completely. Yeah. So that's one way to interpret the error. Okay, so this is a rough outline of my talk. I'm going to show you this empirical study we did, and it's going to convince you, hopefully, that performance, by which I mean accuracy of algorithms, is complicated, hard to understand, varies a lot with a lot of factors that we didn't fully understand. Then I'm going to quote code. So I don't get to do this with such great effect. I'm often talking to privacy audiences, and they don't get what's exciting about quoting code, and you guys do, so I'm happy about that. And then I'm gonna, you know, that's going to be my motivation for thinking about a system that can help us with some of the complexities of the algorithm space. Okay, so part of our inspiration here was actually a kind of self-critique. I spent a lot of time developing new differentially private algorithms, and you know, putting performance numbers in papers and showing that my algorithm is better than a competing algorithm, and started to wonder for myself, you know, am I really measuring things? Can I really tell practitioners this is how this works, and convince them and convince myself? And is the community really assessing our, you know, our work in the best way? And we looked back and found some, you know, sort of self-critique in machine learning. I don't know how many people are familiar with this kind of work, but, you know, there's, you know, results where the machine learning community, you know, asked itself, you know, what are we doing here, and are we really advancing the practice of machine learning? And, you know, things like simple classifiers work well in practice despite all of the really complicated stuff people were inventing. Some algorithm improvements in research papers were completely dwarfed by real-world factors that they didn't take into account. Some people lamented an extreme focus on UCI datasets. That's a particular pitfall that our community was falling into, because we had data sets that a set of data sets that someone would use to evaluate their algorithms, and then the next person who writes an algorithm paper would use exactly those same data sets, and then there's 5 data sets that everybody's using, and there's no variety. And that's one of the things we're going to address.
What is UCI?
Oh, that's the UC Irvine public data sets that are very well known. And yeah, they're sort of benchmark data sets. The UCI adult data set is something that's used all over the place. So they can, you know, particular data sets can get overused. Essentially, what we worried about is that we were actually overfitting our algorithms to the data sets that we were using in these papers, and claiming those as algorithmic advances. And that's a danger. David Patterson has a nice quote where, when a field has good benchmarks, we settle debates and the field makes rapid progress. And that was a part of our motivation as well. And we were also inspired by a website called MLComp, which is unfortunately now, Percy Lang developed this. I think it's sort of defunct now. The observation was that machine learning has a problem where they invent tons of algorithms, and at some point somebody has to help somebody figure out which one of them to use. Now, this was the goal here, that somebody could upload an algorithm and it would automatically run on a bunch of uploaded data sets. And every time somebody uploaded a new data set or a new algorithm, every experiment you could imagine would get run and the results would be right there. And this would advance sort of the understanding of how algorithms perform. One of the wrinkles with privacy is that it's actually harder than machine learning in the sense that we're not allowed to look at the data before we choose the algorithm we're going to run, because the data is protected, right? And we have to pick an algorithm without looking at the data. That's one of the complexities here. So anyway, this is sort of our inspiration. And we also found a kind of symptom of methodological problems. So these are 2 papers. One of them, no, these are 2 papers. Yeah, one is the M1 paper. One's the, oh no, sorry. One of them's my paper, and one of them's the M1 paper. And in both of these papers, we've compared 2 algorithms, the M1 algorithm and this other method, Privlet. And these were the results from the published papers. Okay, this is a graph that's somewhat similar to the one I showed you before, where epsilon is varying here and error is varying here. So if you look at this graph, you see that the M1 error is much higher, consistently higher than Privlet. But over here, you see Privlet is consistently higher than M1. So directly contradictory results. resolution of this, or the explanation of this, is that there's an uncontrolled variable here. I mean, that no one is no one was considering for the experiments. And so this is what we're trying to expose with our benchmark. So it was a Sigma 2016 paper called DP Bench, and an accompanying website, dpcomp.org, that presented the results and tried to make them as accessible as possible to the public. And it consisted of a set of evaluation principles, a set of tools to aid evaluation, and we sort of carried out a big benchmark study. 15 published algorithms from the literature. We evaluated lots of different experimental configurations and tried to do the experimental evaluation in a really careful, principled way. And I'm going to present to you some of the findings, hopefully relatively quickly. Here's some screenshots of the website if you want to peek at it later. So the evaluation principles might seem obvious, but these are the kinds of things that get overlooked, sometimes in a body of literature. So the first principles are like about diversity of inputs. When you evaluate algorithms, you should use diverse settings of epsilon and diverse input data. And we were precise in the paper about what that means. I'm going to show you what I mean by what the key parameters are when you vary data sets for privacy algorithms. End-to-end privacy. So what people can do with privacy algorithms is like leave out key steps or key parameters that need to get set. They'll run a few experiments on the data and then see which parameter setting works best and then pick that one. And that's like cheating, okay? So no free parameters, no side information, no pre-processing or post-processing unless you do it sort of within the scope of your private algorithm with using your epsilon appropriately. And then we need to measure evaluation carefully. We need to measure variability, bias, and compare algorithms in a sound method. I won't get to all the details of that, but they're in this talk, but they're in the paper. So the class of tasks that we focused on are basically computing a bunch of statistics about numerical statistics, so aggregate queries. Think of select, count, star, from, where, and you can have like varying where clauses. So these support like data cubes and marginals and histograms, all kinds of tasks like that on low dimensional data, like either one or two column projections of a larger table or something like that. So here we might take a sensitive data set, extract the gender and grade attributes, and form a workload, what we call the workload of queries. That's the list of counting queries, like the number of female students with grade greater than 93, the number of C students of any gender, that kind of thing. We usually assume that there's a whole list of these queries that the analyst gives us, and our job is to answer all of them with epsilon differential privacy as accurately as possible. One of the principles is to work with diverse data sets. So all these algorithms essentially rely on what's sometimes called a frequency representation of the data. So we have to turn the database, a table, into a vector. And the way we do that is we sort of enumerate every possible record type that could occur in the database, and we then count how many records are actually in the database. So that's the true data vector. So it looks like a histogram. It may be a representation of a multidimensional histogram that's sort of flattened out in my pictures. So the key sort of properties of this vector representation of the data that we identified are the size of the domain. So how many counts are you working with? And sometimes that can be manipulated a little bit if you coarse in the domain. Sometimes you have floating point numbers, and so you have to bucket things, and that will change the domain, and that's a common transformation that happens in these algorithms. So the domain size can change. The scale of the data is what we refer to as the total number of records in the database, which is the sum of all the counts in this vector. And then the shape is essentially the shape of this distribution.
Rather than actually enumerating all possible combinations, all possible conjunctive queries and calling it a separate bin, can't you do some conditional probability graphical model to describe this stuff and say?
You can model the data, and some algorithms do forms of modeling, but this is about the queries that the workload is the queries we eventually want to answer. So the output of the algorithm needs to be
structure could still answer those queries though. It's things like if you're male, given that you're male, what's the probability that you also get a C? If I have a graphical model that describes all those things, I could give pretty accurate answers to it.
Yeah, so it's not the case that every algorithm has to enumerate the domain like this, but for the low domain, for the class of algorithms that we studied in this benchmark, they all did. Yeah. It does break down with multidimensional data, and so sometimes you're forced to essentially factor this representation in one way or another. Yeah. Yes?
Can you explain what are these X1 to Xn?
Those are the record types. So in this picture, it's, gender equals female, grade equals 100, gender equals female, grade equals 99. I'm essentially enumerating every possible tuple that could occur in the projection of the table onto gender and grade. So the size of this vector is the product of the domain sizes of the attributes I'm considering. So the point here is that these are the key properties that we need to vary, and these were not always varied in all experiments. People would pull out real data sets which have some particular scale, some particular number of records, and they wouldn't vary that. They'd vary epsilon, and the shape is really what is determined by one data set versus another that you might find online, or you go to the UCI repository. Okay, so we have a systematic way of varying these properties, and then we did a bunch of experiments. So the algorithms that we considered, this is to some extent a testament of how complex the space of algorithms has become, but I can't explain to you what each of these algorithms does because it would take more time than I have to give this talk. But some of these are naive baselines that you may be familiar with if you've seen some of the privacy literature. What we call identity, which is not a great name, is essentially the Laplace mechanism where you add noise to every bin in this vector. There are extensions of the Laplace mechanism where you try to be smart about what you're going to actually measure with Laplace noise, and then you infer query answers from those measurements. Those can outperform the basic Laplace mechanism. And these algorithms in yellow are what we call data independent. You can prove that the error rates induced by these mechanisms are not influenced in any way by the input data. All right, that's a nice property, but sometimes there's actually added power to this data dependent feature, which is one of the key aspects of our empirical study. So there's other baselines here. Some of these algorithms do some essentially modeling of the data. They try to learn features of the data and then with some portion of the privacy budget, and then exploit those features in later stages of the algorithm. So there's, in 2 dimensions, there's grid-based techniques where you chop up the domain into pieces and you do hierarchies and trees and stuff like that. So I'm going to try to just show you. I'm hoping that these, even though you don't understand the workings of these are sort of like black boxes, you'll still be interested, I hope, in the performance of these algorithms relative to the other and the relationships that emerge. Okay, sorry, I got to go ahead. So the first key insight is that there's a lot of variation with the shape of the data. Okay, so I'm going to show a lot of plots that look like this, and these are algorithms on the x-axis, which I'm comparing for a certain setting, like a given domain size and scale, what the error is like across. Well, this is for one data set. It's called patent. It was the patent data set that we found. But across different data sets, we see how much variation one particular algorithm has, in this case, in error. Okay, so this is really significant because when we run a private algorithm over a data set, we'd like to have some expectation of what the error is coming out. And what this says is that it depends enormously, like an order of magnitude, on some aspects of the shape of your distribution. Okay? Question?
So this, just to check, this would only be true for the ones that were listed as data dependent?
Right, for the data-dependent algorithms. Okay. These are all data-dependent algorithms, actually. Yes, question?
More questions. So in this case, you said that you're looking at range queries, but these range queries compute some kind of aggregate over the range. They say like...
Yeah, the number of individuals whose grade falls into a range, yeah. And it's usually like a workload of such queries, so more than one of them. If you've just got one numerical query to answer, the Laplace mechanism is about as good as you can do. The interesting thing happens when you have to answer a whole bunch of queries simultaneously, which you often have to do in these sort of statistical data analysis tasks.
And can you remind us what you're varying when you vary the shape here?
The shape is like just the shape of the distribution, yeah. Like what it looks like. Is it skewed? Is it dense? Is it, got a lot of holes in it? The truth is, we still can't explain in a nice way what it is about, I have more examples, more things to say about this, about the shape. All right, so this is sort of all algorithms in 1 and 2 dimensions. So we see the variation, there's some algorithms that don't vary as much with the shape, but some that vary enormously, okay? And this is a sort of unpredictability that is a problem for deploying these algorithms. So that's one of our findings. Now, this was also really surprising to us. So we knew algorithms were data dependent, but when we first started working with data dependent algorithms, I assumed that there were some shapes that were hard for privacy algorithms and some shapes that were easy, and that it was something sort of inherent about the data that made that, and we probably can't get around it, but it might be useful to just understand what makes a hard data set, what makes an easy data set. But we found in this empirical study that there isn't such a thing as a hard and easy data set. Or if there is, these algorithms are not displaying that, because some data sets are hard for some algorithms and easy for other algorithms. So what this plot is showing is that the one particular data set, the orange one, is the best case for the Dawa algorithm in the sense that the error is lowest, but the worst for EFPA. Same data set, but somehow these algorithms are exploiting different properties of the shape distribution to get good performance. Question, yeah.
Isn't that exactly what data dependent means?
Yeah, it's not necessarily a bad thing, but it's something that we need to understand, because part of what needs to happen in this deployment is that in a deployment of differential privacy, we need to choose an algorithm at some point. We need to understand or try to predict how that algorithm is going to perform, and the real challenge is that we can't look at the data ahead of time. So it's also, I think, important for the research community. Is our job to find algorithms that work for all data sets or for big classes of data sets, or should we be specializing and saying, maybe I should be inventing algorithms that work for data sets that look like this and find the optimal algorithm for this class of data sets, and then if I'm working with a different class of data sets, I'll choose a different algorithm. That's just not how people are thinking about things yet. And so that's part of the point of this empirical study. Yeah.
When you say you cannot look into the data sets, you mean the algorithm or like the human?
Well, so when the algorithm runs, it's gonna make certain accesses to the data set that are within the model of differential privacy. But if we think about a deployment where Bill's working with a stakeholder that has some data, and they say, I'd like you to help me, run an algorithm over my data and release a set of statistics in a differentially private way. So Bill's got to pick the algorithm. If he looks at the data and picks the algorithm that works best for the data, it breaks differential privacy, or there's some subtlety that could potentially be a threat to differential privacy. And so I'm not sure if that's clear. Some people are nodding, but maybe it's a little bit confusing. But like, you can think of pathological cases where there's two algorithms, and you know how they perform on different types of data sets. And so your choice of algorithm is going to reveal something about the data if you do it in a sort of an optimistic way.
Is that possible? You have a program to pre-processing and choose the algorithm?
Yeah, and so one of the subsequent papers that we wrote was how to choose algorithms from a library of algorithms in a private way. It's tricky because it's hard to bound the potential privacy loss from choosing the algorithm. So we have a kind of method where we learn a bunch of properties of algorithms on like public data, and then we use it to predict which algorithm to pick. I'm not going to talk about that work today, but it's one of the subtleties here. Okay, so the other finding that
Sorry, I know you're not going to talk about that. But,
okay.
But then all of this is the reason why all this is important is because you're making some sort of utility promise to somebody somewhere, right? And
Yeah.
so if you did the algorithm choice in a differently private way, how do you have to modify your assertion about the utility of the result in some weird way as well.
Well, so you're
I don't know what algorithm I picked, but I can still
well.
have somebody use it.
Yeah, I mean, it turns out to be, there's a number of issues here. I mean, for one, it's actually hard to hide the algorithm that you picked because these algorithms have like a set of sort of weird artifacts in their output that reveal the nature of the algorithm. So that tends to be something we don't want to rely on the secrecy of the algorithm we used for the privacy protection. And you're right, at these data-dependent algorithms, the error bounds can potentially reveal something about the data. And that means that, number one, it's analytically, it's hard to even produce these bounds because they're data-dependent and they're potentially sensitive, so you have to use some of your privacy budget to actually release not just what the counts you're releasing about the data, but also the error bounds.
I'll shut up after this, but it seems like we're getting into this minutia where it's almost like we need to proof this against some application scenarios to make sure it makes sense, because now we're talking about, you know, the noise added to the error bounds, that someone needs to make some sort of an actionable decision based on, oh, because I used your tool that helped me automatically select the algorithm versus the obvious thing. Like I was unsatisfied with the obvious thing because maybe the bounds were too wide, but I ran it through this tool to automatically do it, but now you had to add noise to the bounds. I'm just wondering if like what can we say about the application scenarios that really...
Well, the reason the real reason we want to choose an algorithm carefully is because it will give us a benefit of inaccuracy.
How do you convey someone? Don't they have to know that it's more accurate, or else it doesn't matter?
Yeah, and then we, in addition, we will release, you know, some information about the bounds. It could still vastly outperform at the best data-independent method. Yeah, but it depends. So that's what I'm talking about next. So there are these data-independent algorithms that, in this band here, this is a very naive, you know, the Laplace mechanism. This is sort of a better data-independent method, and so this is sort of like a benchmark that if you're going to move to the data-dependent algorithms, you better hope that you're beating the data-independent methods because they're harder to work with. And we found in a number of cases that data dependence really does offer significant improvements, but those improvements break down with essentially the strength of the signal. If you have a high signal regime, either you have a high epsilon budget or a lot of data, you're actually better off using a data-independent method. And so there's this trade-off that you have to be aware of, and that a lot of these sort of fancier mechanisms are being vastly outperformed by the simple data-independent baselines. Yeah, question?
Is there also some like other relation with more dimensions? Because a two-dimensional data set, right, is pretty small in my mind. And I feel like people in the real world have much larger data sets than that.
Yeah.
So is it something where as you increase dimensions, the scale factor matters less and less, or something like that?
Well, I think it's really probably to be more accurate would be the number of records, the ratio between the number of records in your database and the domain size. So the real factor is like as you go into higher dimensions, the signal is getting weaker relative to the domain, and you're going to be more in the low signal regime. The truth is that these smarter algorithms are biased, and what they're doing is they're essentially exploiting properties of the data to give you bias, you know, to exploit bias over variance is what we realized. And this was not at all evident in the research literature. It might be a little bit surprising. And you know, sometimes that's a good thing, but sometimes it can fool you. So some of these data-dependent algorithms are, in terms of absolute error, not outperforming the uniform baseline, which is count how many tuples you have in your database and assume everything's uniform. It's a very naive baseline, and if you probably think to yourself, if that's all I'm learning about my data, this is not a useful algorithm to me, right? So that's a pitfall for research, because if we're coming up with fancy algorithms that are basically exploiting you know, this uniform bias and working well on data sets that have such low signal that they look uniform, we're fooling ourselves, and that's something we need to avoid. Okay, so I'm going to try to move on to the next part of the talk. these are the findings that I've gone over. So we're left, at the end of this. So some of the implementations that we got from other researchers, we re-implemented some of these algorithms. We have this whole benchmark that we ran. We released the code so other people could rerun experiments, or when they invent new algorithms, they can compare with the existing algorithms. And then we realized that the properties of error are pretty complicated. There's all these complicated relationships, data dependence. No single one algorithm is the best. If you want to get the best error performance across the range of scenarios that a practitioner might encounter, you need to sort of carefully choose your algorithm. And so this makes the whole space really complicated. And that motivated our, this is where I quote Cod, because, this is this is what Cod said. Actually, it's not Cod's words. It's somebody writing about Cod, that when Cod was, revolutionizing databases, databases were, without exception, ad hoc, cumbersome, really could only be used by people having highly specialized skills. Which means, to get good performance out of systems in those days, you had to be clever. And that's what we feel about privacy algorithms these days. There are some algorithms that perform really well, but you've got to really know what you're doing and implement them carefully, tune knobs, choose algorithms, avoid pitfalls, all of this stuff. And we want to try to make this easier. You guys are all familiar with the key advances of what Cod did. We'd like users to be able to say, I think this is really important in the space of privacy, to say what they're trying to compute and be divorced from the implementations because they're really complicated. What we want to do is optimize for accuracy, not performance. We want to be able to optimize algorithms for accuracy. And I think we've proposed sort of like a layered architecture where we've hopefully provided useful abstractions. Okay, so our system is called Ektelo. It's meant to be an execution framework, a platform where we can write algorithms and then soon get to optimizing them. And so the way we do this is we write what we call plans. Plans are sequences of operators, and we spent a long time extracting what we think are sort of the key operators. And one of our benchmarks was that we could take our platform and express in it all of the algorithms we had just evaluated. This whole body of code, which was independent, what we called monolithic implementations of algorithms, we want to be able to build each one of those algorithms from operators in an easy way. So the plan is actually executed by someone we call the client, and who's not trusted, and it'll make calls to this protected kernel. The protected kernel is like a library or a body of code that's running that sort of shields the data. So what's interesting are the special operators that take results from the private domain in the protected kernel and ship them to the client. Those are the really critical ones that have to satisfy the privacy guarantee. But what we found is that it's relatively few, and that a lot of the operators are on the client space. And that distinction is really clarifying to have that in your platform, because in the client space, if you screw something up, you don't break privacy, you might screw up accuracy a little bit, but it's sort of a little less critical. We do have a kind of automatic privacy analysis. So if you compose operators together in our platform, you're guaranteed that the resulting plan is differentially private. And some of the technology for this is inherited from older systems like Pink, but it required proving some new aspects of the composition. I won't go into the details here. So our operators are organized into classes. So there's basically 5 classes of operators, and they're colored here to indicate the role that they play. The red ones are the private ones. So you can these are things that run in the private kernel but don't really return anything. And so so those are the red ones. You can transform the data, and it's like a lazy transformation. It happens inside the private kernel, but you don't see the results of it. It just allows you to compute on things in a different form later. We have sort of one classic privacy mechanism, like a Laplace mechanism implemented in a vector form. A bunch of query selection methods, I'll say a little bit more about this, inference, and reduction selection, which is another kind of transformation. Okay, the orange ones are the only ones that consume the privacy budget, because when you implement these programs, you have to be careful about managing the budget and decrementing it whenever you use the data. And so these are precisely the places where we have to prove differential privacy of these components and only these components, and make sure that the budget is accounted for. Okay, so kind of the goal here is to shift the expertise required to build private programs. And so what we envision is so this is, these are the inventors of differential privacy. They're very high on the expert spectrum. And these are, our grandparents who are, no matter what you do, they're probably not going to write a differentially private program. But somewhere in between, we'd like to distinguish between, the privacy engineers that are highly skilled and the plan authors that don't have to have that much skill. The privacy engineers will implement new operators, perhaps, and vet them, prove that they're private, and so on. But the plan authors, who are really the people who have tasks, they know their task well, they know something about privacy, but they don't, they aren't experts. They're just going to mostly compose operators together and then benefit from the automatic privacy guarantee. Okay, so I'm actually going to try to walk through a program as it would look in our framework. Okay, kind of quickly. So this is a plan that computes a distribution of salaries for males in their 30s, and it's going to present that distribution as a CDF, right? Privately computed from a protected data source. So the first line just loads the data. It says in the kernel, in the private kernel, it's going to say load this from a file or something. Then I'm going to do some data transformations. This could have been written in SQL. In here, I'm like filtering, imposing some selection conditions on the data before I query it, because I only care about males who are 30. Then this is a common feature of this class of algorithms. Like I said, I vectorize. So I turn the remaining database into a vector. Again, this happens in the protected kernel, so I haven't released anything, so there's no potential privacy cost at this point.
What's the n parameter?
N is the domain size.
Why do I have to give that as a parameter?
Because you have to decide how many buckets. Essentially, it's saying this is how many buckets I want to, sort of like quantize my data into. Depends on the domain, like what types of domains. But if you have numerical domains that have high precision, then we have to make a choice about buckets. So you might supply that as a parameter.
So the person writing this has to sort of understand the effect of that on privacy.
Yeah.
Okay.
Well, it doesn't affect privacy, but
It doesn't?
no, because you can. I mean, for one reason, we haven't released anything. It's just how you're constructing this vector that we're going to compute on later.
Well, I just always set it to 1.
Because you won't really be able to express your computation over. I mean, a vector of size 1 is just going to be a single count, which is the total size of the database, really.
Okay. So it doesn't affect privacy.
No. So let me try to get through this, see if it makes more sense when I get to the end of the plan. So then we sort of encode the measurements that we want to take. This is a description of of what a CDF is over this data. And then we do some fancy stuff, like this is a domain reduction. One of the data-dependent tricks that these algorithms pull is they sort of like look at the data and identify uniform regions, and then sort of like, you could think of it as compressing this vector or summarizing this vector by shrinking these buckets. So we transform the data through what we call a reduction, and we also reduce the workload. And then we're going to choose some things to measure. We're going to measure them with the Laplace mechanism, and then we're going to do inference to get a consistent data set out. These are all sort of like the types of operations that these algorithms regularly do. And then finally, we return the query answers. So this is, I know there's some details here that probably you don't fully get, but this is a fairly complicated algorithm, one of the state-of-the-art algorithms that's now expressed in about 10 lines of code. Okay?
How do they know to do that, the programmer?
So this is a parameter which is an aspect of this algorithm. It's a parameter that needs to be set. So it's exposed at this level of programming. You can play around with this Or you can have default values. Yeah, question?
So kind of going back to what Bill was asking, so changing the vectorization, it doesn't affect the privacy, but does it affect the accuracy at the end? So that if you vectorize it into buckets, there we go, that are too coarse, then your accuracy would be hurt, though, right? Even though
yeah, I mean, I think the right way to think about this is that you want to vectorize in a way that's consistent with the questions you want to ask about the data. Every bucket in this vector has an interpretation. In the most fine-grained vectorization over a discrete domain like gender and grades, let's say grades are integers between 0 and 100, the finest grained vectorization is going to enumerate every possible combination of gender and grade. If you had floating point grades, or you don't care about full precision on the grade attribute, you could bucket things more coarsely. But that's really sort of should be determined by the questions you want to ask about the data. If you bucket too coarsely, you can't ask questions about sub-buckets. So
where are the domains of the attributes represented? Don't they need to be?
I know you're really concerned about domains from our other conversations. So where's the schema of the data represented?
Well, depends on what you mean by schema. Schema to me is just the attributes, but the domains would be extra. But if you consider that part of the schema, sure.
Yeah. Let's take this offline so I can get to some of the other features of the framework. So one of the key points I want to make is that what distinguishes this algorithm from another algorithm in the literature are these two lines of code. All right, this is the Dawa algorithm, and it has a particular kind of reduction and a particular kind of measurement. There's another algorithm in the literature that looks like this. The only thing that changed is that this algorithm uses a different kind of reduction selection operator and a different measurement. And what's interesting is that the choice of those two operators are orthogonal. So you could immediately ask yourself, well, what if I used AHP's reduction method and the other measurement method, or vice versa? So I mean, you can recombine the operators to form new algorithms that sort of like easily. It's an immediate consequence of our framework. Yeah.
If you rearrange your primitives around like that, do you risk breaking your privacy budget?
I'm not rearranging. What I try to describe here is not a rearrangement, but a substitution of an alternative operator from a class of operators that, like, so this is a reduction selection operator, and there's like a few alternatives of reduction selection. So I'm not reordering things.
I think what my question, maybe what Dylan's question is too, is that there seems to be some choices the program can make here. And there's not a global statement that no matter what program you write in this language, you always have a certain differential privacy guarantee.
Yeah, there is. There is. So any way you compose these operators will be, any program will be differentially private. So what the smarts, well, because this is a share of your budget. So you can't violate your universal budget. What you can do here is you could misuse your budget by, but what's really being expressed here is how much of the share of your budget you want to use.
So if I put epsilon and epsilon there, would I be, oh, that would be equivalent, I guess, to this sort of.
Yeah, I mean, this should really be interpreted as a share. So if you'd probably would like generate an error if you tried to consume more than 100% of your budget.
That was my question. Does the system check that's a total that
right.
you're?
Yes, it accounts for the budget. It doesn't let you overuse your budget. And furthermore, what it has to do, the smarts are in tracing, which is something that Pink did originally, is tracing the transformations you do behind the sort of firewall and making sure that every time you measure a transformed object, the sensitivity is computed correctly and you're charged appropriately for the privacy budget. Now, I mean, you have to vet, the subroutines have to be vetted, right? You have to, at some point, you have to prove something about the operators that are orange, right? You can't just implement whatever you want and expect privacy to hold. You have to prove the privacy of the components, but I think there's a lot of value in being able to show that any composition of proven private components is private. And that really was Pink's contribution. Magda had I think she, are you, yeah.
And also my question was kind of just to follow up to understand the workflow. So like the stakeholder, someone who's not an expert, is going to likely use the system behind some, interface. And as they click and drag things and point and click in that interface, that will fire these kinds of plans that were actually composed by some reasonably good experts knowing what they're doing, saying, I'm going to implement that clever algorithm or that other clever algorithm.
Yeah.
And then your framework will ensure that by doing this, they might misuse or get the worst accuracy, depending on how clever they are, but definitely it's going to be differentially private.
Yes, right, exactly. We're definitely going to give a proof of privacy, and it's still going to, like the plan authors have to have some smarts. I mean, this is not a system that I think is yet designed to support completely naive users. I mean, even in my work with the Census Bureau, if this system fully existed and we could give it to the people at the Census Bureau so that they could try to adapt algorithms to their task, that would be a huge win. I mean, so those are people that are highly skilled. So I think, I may have given the impression I want to support, I don't want to support the grandparents in writing private programs, but it's sort of foolproof maybe because they're not going to violate privacy, but they probably would construct, poor programs.
But what happens if someone constructs different programs and different plans for different queries? Can they get inconsistent answers?
Yes, but inconsistency is something that's dealt with sort of within a plan. So across plans, they could get inconsistent answers. But that's sort of part of life. So I know I'm running out of time, but let me try to show you some of the consequences of writing many of the algorithms that we studied in this empirical study. This is sort of like a very high level view of how the operators, just a list of operators. That's what a program reduces to. Okay, and these are the two programs I showed you in detail, these variants, AHP and DAWA. And these are all the other programs that were in the literature. Okay, so what you can sort of start to see is, and they're roughly in chronological order, so you can sort of see that there's a lot of instances of this sort of plan form where somebody did some measurement selection, clever measurement selection, ran the Laplace mechanism, and then did an inference. And there's, 4 papers that were basically that. And then things got more interesting over here. Well, MWEM started iterating these steps and had a special query selection component. This reduction selection came in. The other thing that we did in our paper is we started doing what we call recombination. We started saying, look, once we've got all these operators, it's really easy to make new programs. So let's make some new programs and show that they outperform the state of the art. All right? And where we're moving with this is to sort of automate that. The other big benefit is that in our code base of our empirical study, these monolithic implementations, there were 18 different implementations of the Laplace mechanism and sensitivity calculations. When these algorithms are implemented in our system, there's only one implementation of Laplace, but furthermore, there's a total of 5 operators that consume the privacy budget and that you need to prove are differentially private. Okay, so I'm running out of time, so I'm probably going to just sort of gloss over the fact that our goal is to accelerate algorithm innovation, and we did that. Mostly we're concerned with innovations that improve error. But we also observed cases where we could significantly improve runtime. And so it's an interesting optimization problem because we have these dual objectives. We have, first, as I said, I think the priority is usually accuracy. But if you can get the same accuracy and a faster program, let's do it, right? So one of our ideas, the optimizer is not built, so we're still thinking about how can we optimize using our framework. But one way to go would be to formulate rewriting rules, and then whenever somebody writes a plan and you match the rewriting rule, you can transform it to a new plan. The interesting questions to ask are when can we prove that a rewriting rule is sort of sound with respect to accuracy, in the sense that whenever I apply that rule, my accuracy will get better, or at least be the same, right? Never get worse. We have some examples of those rules, but we also have some examples where things are really subtle and you can't prove. It's sort of like sometimes it's better, but sometimes it's worse. So you have to think carefully about whether to apply that rule. When the rule be sound with respect to efficiency, Another thing we could do in our framework is kind of like automatically search the space of plans. When I have someone writes a plan, I can take an operator from a certain operator class and tell the system, explore all the plans that make substitutions of this operator from the class. Okay, so I'm going to wrap up. We think our framework's expressive and extensible. You can add operators. You get privacy sort of for free. We have a lot of code reuse, which is, I think, really important because we have to maintain this library of algorithms to support the state-of-the-art body of algorithms. And each sort of component is hard to, we have to be really careful about the differentially private components. We want to prove them correct once and not, 18 times. And we've, made improvements to accuracy just by, reorganizing our operators. Okay, so I'll end there if there's any more questions. This is the empirical study work. This is the work on our framework. The thing I glossed over about how to sort of like do algorithm selection in a differentially private way appeared at the last Sigmon, but I glossed over that.